Hello student, welcome to course PH107. In this lecture we are going to discuss free particle. So I believe that by now you are convinced that time dependent or time independent Schrodinger equation is the ultimate equation that is going to be used to describe the behavior of the quantum particle. Okay, so let's go what we have learned so far. So as I said that we are convinced now that we need to solve time dependent Schrodinger equation to learn about the state of the particle. So this is our time dependent Schrodinger equation in 3 dimension, where I s cross d psi over dt is written in the left hand side and minus h cross square over 2m del square psi plus v psi is in the right hand side. Okay, the time dependent Schrodinger equation in 3 dimension can be written in 1 dimension as follow. So at the left hand side is space independent, so this will remain as it is. Okay, whereas in the right hand side this del square will reduce to d2 over dx square for 1 dimension, okay? And v psi remains as it is. Okay, now we can express our Schrodinger equation as a time independent Schrodinger equation, which you have seen in the previous class, that minus h cross square over 2m del square phi plus v phi is equal to e phi. This is a time independent Schrodinger equation in 1 dimension, in 3 dimension, and equivalently we can write down the Schrodinger equation in 1 dimension, where the del square is replaced by d2 over dx2 as we have seen in the previous slide. Okay, so this is known as a time independent Schrodinger equation. Okay, now we cannot go further with this equation unless we specify what kind of potential we are going to use, or our particle is experiencing what kind of potential. Okay, so we are going to spend a lot of time in solving time independent Schrodinger equation for different kinds of given potential with different kind of boundary conditions. Okay, now another important thing that you have to keep in your mind, that acceptable solutions of this Schrodinger equation phi x must be continuous, single valued, and its derivative must be continuous. Okay, so we will see when we will employ this kind of conditions. Okay, so let's see what is the free particle. A free particle is a particle which experiences no force. Okay, so this is the definition of the free particle. Now let's say we have a potential v of x is equal to v naught, which is a constant. Okay, so now let's say the particle is moving in this constant potential. There is another possibility that this v naught in a specific situation can be a 0. Okay, so under this condition we can say that the particle is free because there is no force acting on the particle and the potential is 0. Okay, so we can write down the Schrodinger equation in a time independent Schrodinger equation as follow. Okay, what I'm going to do, I'm going to take this part v naught phi x from left to right. Okay, so what I'm going to get, I'm going to get e phi x minus v naught phi x. I can take out phi x because this is a common in both the term. So what I will get, e minus v naught times phi of x. Okay, so this is what I have got it as I have stated. Now what I can do, I can take this prefactor minus h cross square over 2m, or let's say h cross square over 2m from this side to this side. Okay, and so I have written down this one. So d2 phi x over dx2 is written as minus 2m times e minus v naught over h cross square phi of x. Okay, now what I can do, I can, just for the simplification, I can coin a new variable for this big name. Okay, so I will call as a k square. So 2m e minus v naught divided by h cross square is replaced by the k square. So now my time independent Schrodinger equation is written in this following compact form: d2 phi o over dx2 is equal to minus k square phi of x. Okay, Now I can take this minus k square phi of x from right hand side to left hand side so that I can make my right hand side is equal to 0. Okay, so that's what I have done it. And now from our previous knowledge we can guess a solution of this double second order differential equation. So let's guess a solution. Phi of x is equal to a times e to the power lambda x, where a and lambda both are constant. Okay, so what we can do, we can now substitute this guessed solution into this equation. Okay, so what will happen when we will take the double derivative of this wave function? What I'm going to get, I'm going to get a e lambda x times lambda when I will take the first time derivative, and when I will take the second time derivative I will get one more lambda. So what I'm going to get, lambda square a e to the power lambda x, or I could say that lambda square times phi of x. Okay, so this is what I have got, lambda square a e to the power lambda x, and in the right hand side I can just put the value of phi of x. Okay, now you could see that this part a e to the power lambda x and a e to the power lambda x are same in both hand side. So then what I could say that lambda square is equal to k square, or lambda is equal to plus minus ik. Okay, so now I have obtained the value of lambda in terms of the ik. So what are the possible solution? In the case 1, when your energy is greater than V0, okay, it means that your k square is positive. Then I can take that lambda is equal to plus minus ik, and then these are the two possible solutions, a e to the power ikx and or e to the power minus ikx, where a is a constant. Okay, now in general when you have two possible solutions, then their linear superposition is also a solution of the same equation. That you have seen when we were discussing about the Schrodinger equation, that if phi 1 and phi 2 are the two possible solution of a wave equation, then a times phi 1 plus b times phi 2 is also a solution of the wave equation. So in a similar fashion we can say that if this and this both are the solution of this Schrodinger equation, then a times e to the power ikx plus b times e to the power minus ikx is also a solution of this Schrodinger equation written at the top, where a and b are the constant. Okay, so this is what we have written it out. Okay, now you can show that this also satisfies the time independent Schrodinger equation in the past. Okay, as we have seen in the previous slide, this is the value of the k. Okay, or we have defined k square is equal to 2m e minus v naught over h cross square. So k will be square root of 2m e minus v naught over h cross square. Okay, it means that after rearranging the term, what I could write that energy is equal to h cross square k square over 2m plus v naught, and in our particular this example, particle is free, so v naught is 0. So this is the expression of the energy. Okay, so where E is equal to h cross square k square over 2m. Now you notice that energy is directly proportional to the k square, where k is, you will see that it's some kind of wave vector, or h cross k will be called as a momentum, which we will see in a moment. Okay, but another important consequence is that there is any value of k is possible, so that any value of energy is possible. Okay, so in this particular case your energy is not quantized, but it is a continuous variable. Okay, now let's ask the first question: is free particle wave function is an eigenfunction of momentum operator? So this is the wave function for a free particle, a e to the power ikx, and this is our momentum operator, what you have seen in the last class, that momentum operator px is defined as minus is cross t or dx. We know that if this function is an eigenfunction of this operator, then it's supposed to give back to the same eigenfunction times some value which we will call as eigenvalue. So let's check it. So this is our momentum operator. I have written down the momentum operator in this fashion from here, and now I have also substituted the value of my phi x, where a is a constant. Now I can take a outside. When I take the derivative of this e to the power ikx with respect to x, I will obtain ik. Okay, so I have obtained ik times this one. This is again my phi of x. I can resubstitute phi of x back, and then you can see that I become I square, which will be minus 1, minus minus will be plus 1, so it will become h cross k times phi of x. So now you have noticed that when you operate momentum operator on phi of x, you have got phi of x back times h cross k, which can be treated as eigenvalue of this function for this operator p of x. So then h cross k can be called as a momentum along the x-axis, and indeed this is an eigenvalue of the momentum operator. Okay, now so this is, we have satisfied that, or we have verified that phi x is an eigenvalue of momentum operator with phi x is an eigen function of the momentum operator with eigenvalue p of x. Okay, now similarly we can show that another solution of your free particle, which is b times e to the power minus I kx, is also eigenfunction of momentum operator, but this time the eigenvalue is minus h cross k. Okay, now let's estimate the expectation value of momentum operator. So this is the definition of our expectation value of momentum operator. You have seen in the last class that expectation value of any operator is defined as phi star operator times phi dx, and if your function is not normalized, then you have to divide by this integral. Okay, right now we don't know our phi for a free particle is normalized or not normalized. We will see in a moment. So that this is the proper definition of expectation value of momentum operator. Okay, now once we substitute phi of x here, so let's see what we are going to do. We know when this operator, momentum operator, operates on this phi of x, what we supposed to get? We supposed to get h cross k, okay, times phi of x. And since k is positive, then we can treat that this wave function or the corresponding wave packet with this wave function is a traveling, right? Okay, so once we have obtained p of x, as I said that once this operates on phi of x, it will give you h cross k back to the phi of x. So the phi star x phi x integral minus infinite to plus infinite dx, and this remains as it is, both get cancelled it out, then we have got h cross k. So the expectation value of the momentum operator is h cross k. Now if you take another possible solution, okay, which is a traveling left, okay, so because here k is negative, you can think of like e to the power I minus k of x is equal to the power minus I kx. So this can be treated as a wave packet which is a moving traveling towards left direction. This is moving or traveling towards right direction, and once you substitute this form of the wave function and estimate the expectation value of the momentum operator, then you will see that it will be minus h cross k. Okay, so now we can estimate what is the uncertainty. So this is what we have estimated. Expectation value of the px is h cross k. Now we can also estimate the expectation value of px square. Okay, we can substitute this px square operator here, and you can do 2-3 steps of mathematics, and then you can see that the expectation value of this operator is nothing but h cross k whole square. Okay, now we can estimate what is our delta of px. The definition of delta p of x is square root of expectation value of px square minus expectation value of px whole square. We know what are the values of these two equations. So then the delta of px is 0. It means that by using the uncertainty relation, delta x is written as h cross over 2 times delta px. So the uncertainty in position is infinite, where the uncertainty in momentum is 0. Okay, so this is the first question of this tutorial. Estimate the speed of free particle based on the present quantum mechanical analysis and compare it with the one obtained using the classical description of the free particle. Once you have obtained both the speeds, now you have to verify whether both the speeds are same or not. If not, then what is the reason behind it? Okay, now let's move further. This is the wave function phi of x is equal to a times e to the power I kx. Now I can write down the complex conjugate of this phi of x is written as phi star of x is equal to a star e to the power minus I kx. Now when I multiply phi star of x with phi of x, what I will get? I will get a e to the power I kx times e to the power minus I kx. So both will be cancelled out, and then I will get a times a star, which I can write as modulus a square. Okay, now by definition this says that the probability of finding a particle which is phi star phi, which is a mod phi square, is equal to a square, which is independent of the position, and a constant value. So this is a constant everywhere. So the probability of finding a particle is constant everywhere. Now I can evaluate the normalization. So phi star phi dx integrated over entire space. I know what is the value of this one from this one. So this comes out this one, mod of a square times. Now this is a ill-defined integral. Okay, so it means that the wave function cannot be normalized. Okay, so the wave function is an eigenfunction of momentum operator. Okay, so the position is delocalized, and that's why the probability of finding a particle is constant everywhere. Okay, now this is your second question. As we have seen that the wave function of a free particle is not normalizable, how to overcome this issue? Okay, because the electrons in solids are routinely represented by free particle wave function, uh, which are used to describe several properties of solids. So the plane waveform of free electron wave function is very useful. Okay, so people have figured it out how to overcome the issue of normalization of a free particle wave function, and you have to state at least one way to normalize free particle wave function. Okay, now this is the general solution of our wave function for a free particle. Okay, now we have seen in previous class where we have discussed time dependent and time independent Schrodinger equation. So the time dependent wave function phi of xt is always written as a product of the time independent wave function phi of x times time dependent wave function, which is nothing but a phase factor written as e to the power minus I e t over h cross. I know what is my phi of x from here. I can substitute the value of phi of x here to get the phi of xt, which I have written it here. Now, because to make it more convenient, I can define my energy is equal to h cross omega. Okay, I can write down energy is equal to h cross omega. So h cross will cancel it out, and what I will get e to the power minus I omega t. Okay, now e to the power minus I omega t I can combine with this one. Okay, so what I will get e to the power I kx minus omega t, and when I will combine with this one, I will get e to the power minus I times kx minus omega t. Okay, so these are the two part of the wave function. So if you look this part of the wave function, then you see that the total wave function is consists of the two parts. One part is traveling left, as we have seen earlier, and another part is traveling right. Okay, so now we can estimate what is the average value of the momentum. So we can estimate the average value of momentum. So this is our average value of momentum, and we can substitute for this general wave function, which consists of the two parts. One is traveling left, and this is traveling right. Once we substitute everything here, so I have written my phi star of x is a star e to the power minus I kx plus b star e to the power I kx. My operator is as it is. I have taken minus I h cross outside, and my phi of x is written here. Okay, now once I will operate this d over dx into this one, I will get ik, and here I will get minus ik. Okay, so what I can do, I can take my ik out, so it will remain positive a times e to the power ikx, and the minus sign is remains here, so it will become minus b times e to the power ikx. Okay, now let me write this big equation into the next slide. So this is what I have written it out. Now if you start multiplying, then what you will get mod of a square. This term with this term will give you mod of b square with the minus sign. Okay, then I will get a star b with e to the power minus 2 ikx, and then I will get b star a with e to the power 2 ikx. Okay, what I have seen it here. Okay, the same will apply to this one. Okay, the only difference here, because here is plus, here is minus, so there will be a change in the sign. So instead of minus, this will be plus. So all the terms will be here in a plus. Okay, now if you integrate, so these terms which are e to the power plus minus 2 ikx, if you integrate, these will be kind of 0, and then the whole thing can be written in a very simplified way into h cross k times mod of a square minus mod of b square divided by mod of a square plus mod of b square. And what we are trying to get, that what part of the total wave function is moving right. So this is the fraction. We can see that mod of a square divided by mod of a square plus b square is the fraction which has a positive momentum, and mod of b square divided by this sum is the fraction which has a negative momentum. Okay, so the total momentum, it consists of the two fractions. One has a positive and one has a negative momentum. Okay, so what we have learned so far? So far we have learned this is our Schrodinger equation. Okay, where k square is defined in this following fashion: square root of k square is defined as a 2m e minus v naught over h cross e square. This was our trial wave function, and once we have substituted this trial wave function, we have seen that for energy greater than v naught, our k square is positive, so that lambda is plus minus k, and this is our general solution of this equation. Okay. Now, if we assume our energy is smaller than v naught, for example, then we are going to get a k square which is smaller than 0. Okay, it means that this term is going to be negative, so I can write down, to make it positive, I have taken the minus sign here. Okay, so I can write down my k is equal to I kappa, where kappa is defined as this quantity, 2 square root of 2m mod of e minus v naught over h cross square. This is my kappa. Okay, so in this case, lambda is equivalent to plus minus I kappa, and then I can write down my wave function c times e to the power kappa x plus d times e to the power minus kappa x. Okay, so I have replaced my plus minus I k in terms of the plus minus kappa. Okay, now we know that our wave function, when x is greater than 0 and when x goes to infinite, our wave function is supposed to vanish. It means that this part goes to infinite, and in the negative regime, when x goes to minus infinite, then this part goes to vanish. Okay, so in the case of energy is smaller than v naught, okay, this is the part of the wave function. Okay, c times e to the power kappa x. Okay, and in another regime, this is the wave function. Okay, so there are two wave functions in two spatial regime, when x is negative, when x is positive. So to write it, the wave function, in a very effective way, we can write in a this following fashion, with the condition that the wave function must be continuous at the boundary mean to x is equal to 0, and it has to be single valued. Okay, so this condition gives the result that c must be equal to d. So if c is equal to d, then we can write down our phi of x is equal to c times e to the power minus kappa times mod of x. Okay, and this mod of x will take care about whether you are in a negative x value or positive x value. Okay, now what we can do, we can try to plot this wave function. Okay, so when we plot this wave function looks like this, which you know that how to plot e to the power minus mod of x type of wave function. And then you will see there's an important issue with the quantum mechanics, that this wave function at x is equal to 0 is continuous, no doubt about it, but the derivative of the wave function is not continuous at x is equal to 0. What I mean, okay, that let's take this wave function. So this is our wave function when x is positive. So then I can take its derivative, and once I take its derivative and substitute the value x is equal to 0, I will get kappa c. And when I take the wave function in the negative x direction, this is my wave function, I can take the derivative, and at x is equal to 0, I will get minus kappa c. Now it means that at this value, the derivative is not continuous, and I can have several values. So it means that kappa c must be minus kappa c if this wave function is an acceptable wave function, so that the derivative of the wave function is continuous. Kappa cannot be 0. Okay, kappa is related to your energy and potential, or let's say the energy. So what it concludes, that for the derivative to be continuous, your c must be 0. Okay, it means that this is not a physical solution. Okay, so no physical solution exists for the case when energy is smaller than V naught everywhere. Okay. However, this does not mean that the solution does not exist if there are finite regions where energy is smaller than V naught, and in another region where energy is greater than V naught. Okay. We will revisit this kind of problem in coming classes, where we will see a region in which energy is smaller than V naught and another region where energy is greater than V naught, and then we will see there are solutions exist which are acceptable solutions of the Schrodinger equation. So in the next class we are going to discuss another problem where you will see some more surprises given by the quantum mechanics. Okay, so see you in the next class.